Before we dive into today's episode, make sure to hit that subscribe button. It's the best way to stay updated with our latest insights.
Ladies and gentlemen, welcome to the CTSS Academy podcast. The energy is electric. The crowd is alive. Let's dive into greatness. We're champions strong.
Before we start the show, don't forget to check our new ebook, Kill All Bugs, Learn Software Testing in One Day. For a limited time, it's only $9.99. Links in description.
Welcome back to the deep dive. Today, we are strapping on our hard hats. We're getting into the absolute bedrock of all digital communication, network topology.
It sounds complicated, but it's really the blueprint of how everything connects.
Exactly. And if you've ever, sent an email, downloaded a file, or even just connected to a corporate VPN, you were relying on one of these blueprints.
A deliberate architectural choice someone made a long time ago.
Right. So our mission today is to cut through all the noise and give you the essential guide to these structures. We're going to unpack the 7 core topologies from the most basic to the most redundant.
And by the end, you should be able to look at a system and instantly get a sense of its strengths and, more importantly, its vulnerabilities.
I like that. So where do we start? What's the fundamental language here?
Fundamentally, topologies just describe the methods in which all the elements of a network are mapped out. But the crucial thing to grasp right away is that there are 2 main types.
2 types that sound similar but are very different.
Very different. First, you have the physical topology. That's the actual tangible arrangement. Think of it like the layout of a road network.
Where the actual cables are run, where the computers physically sit.
Precisely. And then there's the logical topology. This describes how the data actually flows on top of that physical setup.
Okay, so it's the difference between the street map and the traffic laws.
That's a perfect analogy. The map versus the direction of flow, the speed limits, all of that is how the data behaves.
I love that. So the physical layout is the potential, but the logical flow is the reality. We're going to focus mostly on the physical blueprints today.
Right, because that's where the real architectural drama is.
We've got a lot to cover. Point-to-point, bus, ring, star, mesh, tree, and then the hybrid model. We should probably start with the simplest ones.
The ones that almost feel like historical relics now.
Let's kick off with point-to-point, PTP. This has to be the easiest design you can imagine.
It really is. It's just a single, dedicated, direct link between 2 computers.
And that's it? That's the entire network?
That's the whole thing.
Yep.
And its strength is that absolute focus. Because the connection is direct, it's incredibly fast and highly reliable.
No shared path, no contention for bandwidth.
None at all. And from an organizational standpoint, it's really cheap and easy. You don't need a dedicated server or a network operating system.
Or even expensive technicians, right, because the users just set their own permissions.
Exactly.
So why isn't every small office just a bunch of P2P links then? What's the trade-off for that simplicity?
Well, the first killer is scalability. It just doesn't scale. You can only use it for very small areas where computers are literally right next to each other.
Okay.
But the bigger issue is you sacrifice any kind of centralization. There's no central place for file backups, for uniform security, for management.
So you're just relying on the security decisions of the 2 people involved.
You got it. It's not going to run your corporate headquarters, but
Yeah.
you do still see P2P connections used in specialized areas, like linking a control terminal directly to an industrial machine, where that reliability and speed are absolutely critical.
And the systems are physically close. Oh, okay, that makes sense. Now let's move to the bus topology. This one feels like the first real attempt to scale up from just 2 devices.
It was. Historically, it was a massive step. The bus topology uses a single cable, sort of like a highway or a spine.
And all the nodes, all the computers just tap into that one common line.
Right. And if that spine has 2 distinct endpoints, we call it a linear bus topology. This structure basically defined early local area networking.
And I'm guessing the big selling point was just cost.
Absolutely. The cost of that one cable is very low compared to other setups, so it was inexpensive and really easy to install.
It's also a passive topology, which is a key concept.
Very key concept. It means the computers only passively listen for data being sent. They don't boost the signal or actively participate.
They just wait for a data packet addressed to them to fly by on the wire.
They're just eavesdropping, essentially.
But waiting on that common cable is exactly where the whole system breaks down, isn't it? This is where we hit the fatal flaw of the bus.
Precisely. The single point of failure that, it ruined so many early networks.
So what happens?
If that common spine cable fails or gets severed anywhere along its length, the signal path is broken for every single device.
The entire system just crashes.
The whole thing goes down. Think about early Ethernet with those thick coaxial cables. If someone just stepped on the cable too hard, or a terminator cap came off the ends,
The whole department was down for the count.
for hours sometimes, it was brutal.
And that vulnerability, plus, as soon as you tried to scale it, you ran into huge performance issues.
Oh, definitely. When network traffic gets heavy, you get collisions. Two devices trying to talk at the exact same time on that one shared line.
And every collision just tanks the performance.
Significantly, it's like a large group conversation where everyone is shouting across one table. It just becomes noise.
Plus, the cable itself has a limited length, right?
Strictly limited. The signal degrades over distance, so that imposes a really harsh physical boundary on how big your network can even get. The bus taught us that shared media was a huge bottleneck.
So because the bus failed so spectacularly under pressure, designers had to find something better, something with more structure.
Which brings us to the ring topology.
Right. The layout is different. Every device has exactly two neighbors, and the last one connects back to the first, forming a closed loop, a ring.
And here we shift from that passive model of the bus to an active one.
What does that mean, active?
In a typical ring setup, messages travel in one direction, and they use a special packet called a token.
Ah, the token.
Yes, only the computer that is currently holding the token is allowed to transmit data. Once it's done, it passes the token to the next device in the ring.
That sounds much more orderly. It guarantees equal access for everyone, and it prevents those awful collisions we saw with the bus.
It's a very clean system. And because every node is actively receiving and then regenerating the signal before passing it on, you don't have the same length limitations as the bus.
And I imagine it's easier to find problems.
It could be. For instance, it allowed for faster error checking. Because if the token suddenly disappeared, you knew instantly there was a problem somewhere in the circuit.
Okay, so it solves collisions, it extends the range, but it fell out of favor pretty quickly when modern Ethernet came along. Why? What was the catch?
The complexity of managing that token just outweighed the benefits. And while the ring is great with high traffic, it's incredibly fragile physically.
So a single point of failure again.
A different kind, but yes, a single break in that ring, a broken cable, a failed computer, it breaks the entire closed circuit. The token can't circulate.
And the whole network is dead.
Exactly. And troubleshooting was a nightmare. You had to trace the token's path all the way around the loop to find where the failure actually was.
So modern high-speed Ethernet, which is based on the star topology, just offered a much simpler way to do things.
A much simpler way to manage contention without relying on this constantly circulating mission-critical packet.
Okay, so the bus taught us that shared media fails, and the ring taught us that complex circulation fails. That brings us to what's in almost every modern office building today, the star topology.
The star is all about centralization. Instead of connecting to a shared spine or a loop, every computer connects directly to a single central node.
Usually a hub, or these days more likely a switch.
A switch or a concentrator, yeah. And it's so popular because it maps perfectly onto the structured cabling layouts that are already used in buildings.
And this is where you get a huge structural advantage. Resilience at the edges.
What do you mean by that?
Well, if iComputer's cable fails in a star network, only I go offline. Everyone else is fine.
Exactly. Only the failed node is affected. Adding, deleting, or moving devices is also incredibly easy. You just plug or unplug a cable at that central hub. No one else is disrupted.
But that centralization is also the big risk, isn't it? The Achilles heel of the star.
It is. You hit on the key trade-off. If that central hub or switch fails, every single attached node is instantly disabled.
So you've traded the distributed risk of the bus for a single catastrophic point of failure right in the middle.
You have. And that makes the choice of that central device so important. The installation cost of a good switch could be high, and the network's entire performance rests on its capacity.
If you get a cheap, dumb hub, performance will suffer.
But if it's a powerful managed switch, the network can absolutely fly.
All right, so we've gone from simple links to centralized control. Now we get into the really advanced stuff, the expensive but ultimately most robust architectures. Let's talk about mesh.
Mesh. If you need a network that absolutely positively cannot fail, you build a mesh.
And why is that? What's the design?
Mesh is the absolute pinnacle of redundancy. It works because each computer connects directly to every other computer on the network.
Wait, every single one?
Every single one. You're essentially building a massive web of dedicated point-to-point connections between all the devices.
That sounds geometrically complicated. The benefit is obvious. You always have an alternative path for data. But the infrastructure cost must be insane.
It's exponential complexity. There's actually a formula for it. If you have n devices, the number of cables you need for a full mesh is n times n1 divided by 2.
Okay, give me an example.
Sure. If you have just 10 devices, you need 45 separate physical cables.
Wow, okay.
Now scale that up to 50 devices. Suddenly you need 12,225 cables.
That clarifies things. Installation must be a nightmare. You'd need huge amounts of physical space just for the wiring.
It's reliability at any cost.
Yeah.
And we do differentiate between two types. There's full mesh, which we just described, used in really high-stakes environments.
Like military command systems or financial exchanges.
Exactly. And then there's partial mesh. That's a compromise. Most devices are fully connected, but a few peripheral ones might only connect to 2 or 3 others.
It's a way to get some of the redundancy without the full astronomical cost. And the benefits, besides just robustness, must be huge. No traffic jams, right?
No traffic problems at all because of those dedicated links. It's also easy to find faults, and you get incredibly high privacy and security.
But that initial cost, it's the most expensive and most complicated implementation out there.
By far.
Okay, moving on from the web of mesh to the hierarchy of the tree topology. This one feels like it's based on an org chart.
That's a great way to put it. The tree structure is hierarchical. It starts with a single root node and then branches out.
And it integrates various star topologies into a single bus structure.
It does, which is why it's sometimes called a star bus topology. It really lets organizations mimic their corporate structure right in their network design.
And the advantage of that is control. If a node fails down on one branch, it never affects the rest of the network.
Right. And expanding a department is fast and easy. Error detection is also more manageable than in a pure bus network because you can isolate the failure to a specific star segment.
But it has challenges from both its parents, so to speak.
It does. It's a heavily cabled topology. And because it relies on those central hubs for each star, if a high-level hub fails.
Everything beneath it in the hierarchy is disabled.
Correct.
Yeah.
And maintenance gets really difficult if you start adding too many layers or nodes. It gets messy fast.
Which brings us to the final pragmatic solution, the hybrid topology. This is for when no single pure design meets all your needs.
The hybrid is just that, a mix and match, combines 2 or more standard topologies in a way that the result isn't any single one of them.
Can you give an example?
A classic one is a large university campus. The core backbone connecting all the buildings might be a highly reliable ring.
Okay.
But inside each individual lab or on each department floor, they'll use the much easier to manage star topology.
So the biggest payoff here is just pure flexibility.
Flexibility, scalability, and efficiency. Hybrid networks are so effective because you can tailor the structure to the need. You use a high-cost, high-resilience design where data is critical.
And a low-cost, easy-to-manage design everywhere else.
Exactly. It also tends to offer the easiest method for error detection because you can logically isolate a problem to its specific topological segment. Is it in the ring backbone or the star lab?
The trade-off, I assume, is once again cost and complexity.
Of course. The design is complex, and managing multiple different standards at once can make it one of the costliest processes to implement and document properly.
This all raises the big question for you, the listener. When an organization sits down with a budget and a list of requirements, how do these trade-offs lead to a final decision? What are the key drivers?
It really all comes down to cost versus consequence. If the absolute #1 priority is the cheapest possible installation.
Which is pretty rare these days.
Very rare. But you go with the bus topology. If you need shorter cables, easy expansion, and you're using modern twisted pair wiring, STAR is the default choice.
STAR really has won the commercial battle, hasn't it?
It has, because it's resilient enough for most localized failures, and it's so easy to troubleshoot.
So STAR is the default for most businesses. But when does reliability just outweigh every other factor?
That's when you look at mesh. It's for when downtime is literally not an option. A full mesh is theoretically the ideal choice, but its cost limits it to those mission-critical contexts.
And in the real world, most large networks are a mix.
Most large enterprise networks today are a hybrid. They'll use a high-speed redundant backbone that might look like a partial mesh or a tree for the core.
And then deploy start topology switches out to all the end users.
Exactly.
That's a huge stack of information, but it gives us a real appreciation for the hidden architecture driving everything we do online. We've gone from a simple P2P link through the historical fragility of the bus and the ring,
All the way up to the centralized reliability of the star, the sheer cost of the mesh.
the hierarchy of the tree, and finally the flexibility of the hybrid. It really hammers home that network design isn't an accident, it's a series of calculated compromises.
And that compromise is where all the insight lies. You know, the fundamental difference between a robust network and a fragile one often just boils down to one question.
Yeah.
How many single points of failure does it have?
Right. Whether it's the common cable in the bus, or the fragile loop of the ring, or that central hub in the star, understanding the physical topology lets you instantly assess the hidden resilience of any system.
That's a fantastic takeaway.
So here's a thought for you to take away. Next time you encounter a modern cloud architecture or some hyper-distributed system, ask yourself, have they really applied these old lessons learned from the bus and ring? Or have they just created a new, unseen single point of failure somewhere in their logical architecture? Because ultimately, the shape of the network dictates its destiny.
Thanks for listening. If you found value in today's episode, please subscribe and leave us a review. It helps more people find the show. See you in the next one.
Hey, yo, haven't you checked out our new book yet? Link in description.